was going to solder here.
Is there any more?
Give him a second.
You need a fan?
You need a fan? There's a fan there.
Should be fun.
All right, some tips on debugging the circuit. There's a little chance that the first shot it works. Right? Usually, not even happening to me. Work for you, Steven?
Oh, no, I'm not even close.
So, several things. If you finish the soldering, it's not working. Starting with the power supply. Okay. Something you need to know. USB ports, no matter it's a micro USB, USB-C type, USB Arduino type. I don't know what's the name of it. The big square one you guys are using. It's gonna be 5 volts. So all the USB ports are 5 volts. Everybody needs to know that. And where's the USB port? It's right here. It's right here. If it's not working, you want to start probing this pin, and because that's directly power supply. If you plug in the laptop or desktop, that's a 5 volts from the computer. And that's the fuse. The fuse is just protecting the circuit after this line. So it's basically just a wire. In that case, it's not supposed to drop any voltages. So you got 5 volts from the computer. You are supposed to get 5 volts over here. Probe it. It's not 5 volts. You want to fix that first. So if, for example, I probe that, I get everything soldered, I plug in, and none of the LEDs are on, and it's showing like a 3.5 volts. What's the first thing you want to check? What's the reason for that usually? It's dropping, right? So when it's dropping, which means there will be some short circuit or short path to ground somewhere in your circuit. Because it's not exactly 5 volts anymore, and it has a short path, which means a low resistance path to ground. So it's actually drawing a lot of current from the 5 volts power supply from the computer. It's dropping that voltage from 5 to like 4.2, 0.5. And that will be a problem. You have to figure out where the short circuit is in your circuit before doing anything else. You want to unplug it first and then start debugging, because it's going to cause issues. High current can burn circuit components. Okay? And your LED over here, that's the power indicator. No matter what you plug in, if you have a decent 5 volts, an LED should show a really solid light displayed on the LED. Because there's nothing else. It's just the 5 volts and current limiting resistor and the LED, and go to ground. So at least this should be turned on. Okay? If it's not, unplug it and start debugging the issues. Another thing is, for the connections on the board, if you don't know how to debug it, there's a very handy tool for all the multimeters on your bench, and you should know how to do continuity check. If you don't, ask around or ask me. Okay? You must know how to do continuity check. That's a very basic tool to debug your board. Very important. And for the rest, for the other parts of the circuit, like this is the IR receiver, IR transmitter, the filter circuit with the microphone, the RGB, LEDs. So these are all peripherals for the following labs in the semester, and they're not really functional modules to keep your microcontroller programmable, right? So you don't have to really debug these ones if you don't have time before the deadline of the first lab. They're not really doing anything. But this is an audio amplifier. I'm recording. If you forgot, just come back to the video, okay? So this is the audio amplifier, and you need to ensure that it's functioning, because that's a lab due next week. Remember the demo I showed you guys in the lecture on Monday? It's a speaker with a Morse code, and this has to work so you can play something to the speaker. And the speaker is connected to these terminals, and the input is being put into this input of the audio amplifier. You make sure that if it's not working, you want to probe first. You want to probe the power supply, since it's getting 5 volts. I want to check the continuity things of the pins and make sure this works. Okay, but nothing else is really doing the audio amplifier, audio playing functionality. So if this works, and the microcontroller is programmable, and you should be able to do the lab 1 or tutorial 1, which is due next week. Okay? And this is the USB to UART converter. The USB data comes in from these 2 pins, and the power supply is the ground. And one little thing here, maybe on the quiz in the future, you can see this is the ground from the USB, and it's definitely connected to the universal ground of the board. As you can see, it's actually connected to the one end of the little inductor here. It shows the L1, so all the L's are inductors. So it's shorted to one terminal, the other terminal of the inductor. But however, the opposite side of the inductor is shorted to ground. So it seems like the USB's ground is not shorted to the universal ground. Is that the case? Do you understand what I'm saying? Everything should have a common ground. However, the USB's ground is not really shorted to the common ground of the circuit. Is that the case? That's a really, really important note you need to know. Since I had issues with a commercial product I developed 2 years ago, and that solved a lot of problems. Okay? So what's happening here? What is an inductor? You learn inductors in circuit 1, a little inductor. So inductor rejects what and conducts what? Inductors. Like capacitors reject what and conducts what? So capacitors rejects DC signals and passes AC signals. And inductors are on the opposite side. It's a coil, right? Think about it's a coil. It's a coil, it's basically a wire, but being wounded as a coil, okay? So if you have a static voltage or current, it actually passes that perfectly. But AC is alternating, it starts rejecting it, right? It's creating a magnetic field to rejecting the existing current. So inductor being put in there is actually trying to transmit DC 0, right? Here's ground. Ground is 0 volts. Inductor, 0 volts ground is actually DC 0. So DC 0 is going to pass through this inductor and reaches here. So it's not actually affecting DC 0. But it's rejecting what? It's rejecting AC noises. There might be some AC noises from other components being shorted to the same ground, and that AC noises are not getting through that inductor, which is going to affect the ground of other components of the circuit, which is giving you a very solid 0 DC ground. It's not fluctuating, which is very important. You need a solid DC ground to make sure everything is at 0 volts. Okay. That's why they put a little inductor there. But if you remove the inductor, just short everything to the same ground, you are probably not seeing any differences. But it's just improving the performance under AC noisy environment. That's something you need to know. And a lot of components over here are not super necessary for the functionality of the circuit. If you remove them, you can still program it. It still works. It's still gonna work. Like these capacitors, you can see a lot of capacitors are. The one terminal is connected to power supply, and the other terminal are shorted to ground. You can see a lot of capacitors are doing that. Okay, so all of them are noise rejecting capacitors, because it's you can imagine I want to provide a super solid DC voltage to the power supply. So if there's a little bit of fluctuation of the DC voltages, the capacitor will absorb it. It's like you have a huge bucket. If there's a little noise of the water input, it's actually not changing your DC or the volume of the bucket really much. So all these capacitors being placed in these positions are doing that job. You can see a lot. There are like these ones, you see? This guy and this guy. As one terminal shorted to ground, another terminal shorted to the DC power supply. Doesn't matter if it's the 3.3 volts or 5 volts power supply. They are doing all the same job. And sometimes you see capacitors with different values, and they are rejecting different frequencies of the noises. But they are doing the same job. If you don't have it, it's still gonna work. Just let you guys know. It's just improving the performance under noisy environment. So this is a USB to UART converter chip, and it's pretty difficult to solder. Make sure you know what you are doing. You have to use a hot air to blow it, and there are some tips on how to solder that. If you've never done that before, you can ask me. You can ask Gavin, Kai. Maybe Steven also has some experience. You can ask us. So don't just give a lot of heat on it. It's going to delaminate the pins. If you delaminate the pins, you spend like 3 days on the board and have all the rest of the components soldered on the board. You delaminate that pin, these pins on that chip. You have to redo everything. I have to give you a new board over here. I have to redo everything. Seriously. It'll be really frustrating. So make sure you know what you're doing. And that's one of the difficult part to solder. And this one is not that bad because the pins are outside of the chip, not directly underneath it. But the thing is the pins are so close to each other. And I showed how to do it for Gavin. And so Gavin, Steven, Kai can also help you guys how to solder that 100 pin microcontroller. Make sure you do it right. Okay? And other than that, you'll see these two components. This is the SD card socket on the back, and this is the SD card's voltage shifter, because the SD card is taking 3.3 volts. However, the microcontroller is outputting a 5 volts logic. Okay? So you have to understand that. This is another, embedded system 101. You have to know it. Every single thing I'm talking about in this class right now is important. It's like embedded system 101. You need a level shifter because this interfaces with your microcontroller, which is taking in 5 volts logic, 1 and zeros from 1 to 5, and it converts the 5 volts logic into 3.3 volts logic, and so these pins are shorted to this SD card's socket. I mean, it's an SD card socket. You plug in the SD card into the socket, so actually these are directly interfacing with the SD card. Make sense? So you can consider these are basically the pins of the SD card, because that's a socket. Okay? So that is why you can consider this guy as a SD card, because all the pins are shorted to the SD card's pins. So you can see the 3.3 volts, these are the digital pins, and all these need to be 3.3 volts logic. And this is the level shifter. Here is taking in 5 volts logic, convert them into 3.3 volts logic. And that's the SD card module. And this is another filter, and very interesting topic on that. It's called digital design, directed digital synthesis. Another super important technology. We haven't developed that lab yet, but I'm going to do that. One quick example. If you see the function generators are outputting sound waves with different frequencies and amplitudes, they all use a technology called DDS. It's directed digital synthesis. And the quantum computers are taking all these RF signals being synthesized by FPGAs using DDS. So you can synthesize different frequencies and amplitudes for inputs of quantum computer. So very important technology. I think we need to learn, because advancement in quantum computing, you guys need to know what's really happening on that as well. So job opportunities in national labs if you know how to do interfacing signals with quantum computers. So not really too much. That's it, right? So if you have this part soldered, you got power supply, you got an LD indicator, you don't really need anything here to be functioning, and you should be able to program it. And if you plug in, you are not seeing a board displaying your IDE, which means you haven't downloaded the software package called the bootloader yet. I think Kai has a tutorial. I'm gonna upload that tutorial to Canvas, so you can follow that tutorial to download that software to your board, so you can program it. That's it. Any questions? I'll let you guys keep working on it. Okay, I'll be around. Give me a second. Let me turn this